Let's start applying our differential equations. The most common first example, one we actually did back in chapter 3, is based on population growth. Gestational period for a field mouse is 3 weeks. Usually population increases about doubling every week. So let's make that assumption that the change in population is double time in weeks if a field is known to have about 150 mice. What's an expression for the population t weeks from now? Oh boy. Advantage 1. We did this, chapter 3, section 8, applications of exponential functions. So I know the answer should be something exponential. But that's an assumption. Leo?
Would 150 be a p-value plug in?
150 would be a?
We go into value p for t.
It's got to go into one of them. And that's mice, t is weeks. So that should be a population value. So let's assign it to a time. Well, that's the population right now. Let's assign that to the time 0. And then that can be an initial condition, a boundary value in this differential equation that will allow me to solve for an appropriate constant when I do what we were doing last week and treat this as separable. So if I write dp dt equals 2p, I can separate this exactly as we did last week. dp over p is 2 dt. And now, to do separable equations, I separate and integrate both sides. It's the integral on the left.
The L and the after that p.
And on the right?
T plus c on the right side.
Great. Now, I could go right here, put in the time and the population, and solve for that c. But I prefer to write an explicit equation where I can first. So I'm going to get rid of the logarithm on the left side by exponentiating. Now we did a trick when we were adding with exponentials.
You multiply e to 2t then times e to c.
And since e to the c is again a constant, I can just make that some other capital K, capital D, pick a letter, I don't care. And I can say that the population is a e to the 2t, where a is that number e to the c. You'll notice that the absolute value disappeared. I promise I didn't do that arbitrarily or capriciously. E to the c is always positive, no matter what c is. But A could be positive or negative, and that allows me to take care of the absolute value on the right-hand side. So really over here, I'm going to put plus or minus to account for the absolute value. Now I'm going to put in my initial condition, and instead of solving for C, I'll solve for A. Same idea. Population at time 0 is 150. And on the right-hand side, A times e to the 0. E to the 0 is 1. I know A. A is 150. Assuming this model is correct, what is the population of mice in this field in a month?
50 equals to 60 times 150.
I don't know where you got 60.
I'm doing T is 30 days per month.
But T is in weeks, not days. So I'm going to use 4 weeks for a month. And then I can say my population somebody give me a number. No, I mean this number. Good answer, though. I like that.
147,143.6981.
447,000. What was the rest of that?
143.69.
What am I? My field is overrun with mice. This is not wrong. It's just not realistic.
If we're doing this on an exam, would you want us to mark down the 0.7 of the mice?
No. As a matter of fact, if you'd written 447,000-ish, I'd be okay with that. As a matter of fact, this answer is perfectly fine. I just wanted a feel for what this number was and realized that I started with 150 mice. And a month later, I have 450,000. Doesn't make sense. I mean, literally, you wouldn't be able to walk through the field. It'd be a giant field of squirming mice, like the snake pit in Indiana Jones, the first movie. The floor is moving. No, it's not floor. Same idea, it's mice. This doesn't make sense. What's the problem here? The problem here is reality. Reality doesn't support 450,000 mice in the field. There's some limitation to the amount of food available, the amount of space available, the fact that if you've got a field with 400,000 mice, they're going to be everything that eats mice is going to come there. You're going to have owls and hawks and everything swooping down on this field all day long. So there's some other limitation involved here. And this model that we created is a model of unrestricted growth, which is in some sense unrealistic, but at the beginning, fairly accurate. Now, we mentioned this not last week, but the week before, when we were first talking about differential equations, we were looking at the slope fields. If we were to draw the slope field for our original differential equation there, we would see an unstable solution at 0, and everything blows away from 0 really quickly. But I would expect that there's some limitation to what my field can hold. Let's change our model. There's a lowercase k and a capital K. I apologize. I didn't come up with the letters. They're in the book that way. I would happily change that other second K to some other letter. It doesn't matter. But let me think about the slope field, because notice this is an autonomous differential equation. Just like this one was, there's no extra factor of t over here. As a matter of fact, when I wrote it down here, I didn't even put of t. Everything on the right-hand side is in terms of just p. Here, everything on the right-hand side is in terms of just p and some constants. There's no t over there on that side. So this is autonomous. Which means I know what the slope field looks like if I can figure out where the equilibrium solutions are. I can tell you what kind of equilibrium solutions I have. Where are the equilibrium solutions? What are equilibrium solutions again? Where the slope field is not necessarily stable. It could be stable, it could be unstable, it could be something else, where I have a slope of 0. So all I have to do is set that equation up there to 0, and I notice that happens in exactly 2 places. K is a number, it's not 0. P could be 0. Or 1 minus P over capital K could be equal to 0. Oh, wait a minute. That happens when P is equal to K. So I have 2 equilibrium solutions, 0 and K. I am going to make a dramatic assumption that K is a positive number. That'll put it up here somewhere. And now the question is, what's the slope field look like? Now, if we picked some numbers, we could actually draw this on the computer. I'm going to cheat and not pick any numbers. I'm just going to look with some ideas here. Let's suppose that P is a negative number. If P is negative, when I put a negative in here, I'll have 1 minus a negative. That term will be positive, but this will be negative. Positive times positive means negative. So down here, I know the slope is going down. I have no idea how steeply it's going down. And for the moment, that doesn't matter. What if I pick a number between 0 and P? Let's pick exactly half of P. What happens? I'm sorry, that's not P over 2, that's K over 2. Exactly half of K. Helps if I write down what I'm talking about. Okay, wait a minute. That makes this a positive number. What's that do here?
Get product number two.
K over 2 divided by K is going to be a half, isn't it? So this is 1 minus a half. This is positive 1/2. This is positive. This is positive. My slope is going up. That number is never 0 between 0 and K, which means it's got to be positive everywhere in there. Every arrow you draw in this strip must be going up. What does that tell you about this equilibrium solution?
The equilibrium at P equals 0.
Right, but what does it tell me about the equilibrium at P equals 0? Remember, we had categorizations. It would be unstable. Because we don't get closer to that one as time goes on, we get further away from it. If we're a little bit below it, we get further away. If we're a little bit above it, we get further away. So I get stuff going away from that horizontal line. What if I pick a value above K? Oh, wait a minute. This is positive. But if this number is bigger, P is bigger than K, then this fraction is bigger than 1. 1 minus something bigger than 1 is negative. These slopes go down. So what happens at this equilibrium solution? It's stable. Which means I can now tell you that as time goes on, I have a horizontal asymptote at capital K. There's an upper limit to how much I can have. Say that again. The carrying capacity. The capacity of my field to hold mice. The capacity of my lake to hold fish. The capacity of the environment to support the population I am doing. Now, on page 612, they picked numbers. Little k is 0.08, capital K is 1,000. There's my stable asymptotic equilibrium. There's my unstable one. Notice they didn't even bother to draw what was going on when P was below the y-axis. Sorry, the x-axis. How do you have a negative population? Doesn't make sense. But now I could say, all right, let's draw curves on here. I said we started with 150 mice. I would be here. I'd be going up. And then as time gets further and further on, I start to settle in towards this asymptote. I would see for different starting values, curves that look like these. Notice when my population is too big, it falls towards that carrying capacity. When my population is small, it grows and then it starts to taper off to reach this theoretical capacity. I claim that I didn't pick P over 2 randomly. If you look at these curves, you'll see they start out shallow, they get steeper, then they get less shallow. Sorry, less steep, more shallow. That means there is a fastest growth somewhere in there. Means this curve is switching from concave up, concave down somewhere. There's an inflection point in this curve. It turns out that inflection point always occurs halfway up. Now, we could actually do that by taking the derivative here and using the chain rule. It's a long pain in the ass calculation. I don't think it's worthwhile, but I guarantee you that the inflection point on any solution curve happens halfway between those two equilibria. Like I said, I could do the calculation. I don't want to. So how can I prove that that is where I have a maximum rate of growth without doing the calculation? Ready? All the way back to chapter 3, calc 1. I want to know where my derivative has a maximum. My derivative has a maximum where its physical graph has a maximum. Okay, wait a minute. This is the equation for my derivative. What is the highest power of P in this equation? If I multiplied all that out, that's a quadratic equation. What's the graph of every quadratic equation look like?
Maybe like a parabola like this.
Wait a second. It's either a parabola that opens up or it's a parabola that opens down. How do I know which one?
Depending on the x squared, negative or positive.
And that x squared is negative,
It would be like this.
which means it has a maximum. But parabolas are symmetric, aren't they? It's a downward opening parabola. And what's more, I know where its x-intercepts are. I know where that parabola is equal to 0 because you figured that out up here. It's 0 at 0 and k, capital K. But it's also symmetric. Where's the middle? Exactly halfway between, and that's got to be the vertex. Maximum at k over 2. Now, if you really, really want to see it, on page 613, they did the calculation the long way. I think I'd rather hit myself in the head with the textbook. It'll hurt less. Questions? Yes, sir. Then I'm going to have a different problem, but this particular equation does go through zero. If the equation went through some other thing, it would be exactly halfway between the roots, right? Because it would be symmetric, because it's a parabola. But one goes through zero, so I knew it was going to give me that one. That's the best part about this particular differential equation, is that it's based off of the one we did before. And if you have a population of zero objects, spontaneous generation doesn't work. More questions? This equation is separable. There are no t's over there. A bunch of numbers, but there are no t's. And if it's separable, we can solve it. Means I can come up with the equation for this curve here. I can figure out what this equation looks like. And then I can actually go a step further and figure out what that equation is. But in order to separate this equation, I end up with dp over p times 1 minus p over capital K equals little k dt. The right side's a piece of cake. The left side sucks. All right, if the left side sucks, I need to fix it to make it less sucky. I'm going to multiply by capital K on the bottom and the top. So I get K dp is P times capital K minus P. I just distributed the K on the bottom into this factor. Now, why would I do such a thing? We do such a thing because the right-hand side is trivial. It's only this left-hand side that I have to worry about doing the integral of. But this is partial fractions. I know partial fractions. Chapter 7, section what? 3, 4, way back there. We did that in September. Okay, solve for A, solve for B. I cross multiply. I get A times capital K minus P plus B times P equals K. There should be a dp on the end of this. If I put in P equals 0, what does that tell me? Because I will get 0, Ka equals K. Perfect. If I put in P equals K, what do I get? because that means this left-hand side just became 1 over p plus 1 over k minus p dp equals little k dt. Now remember, little k is my growth rate. Like we said with our field mouse population, the field mouse population doubled every week. That was the little k. Capital K is the limitation, our carrying capacity in some fashion. I need to use that to figure out my upper threshold, which I may or may not know in advance, but somewhere somebody has to give me some more information. Integrate. What do you get on the left? Yeah.
Be like ln of the absolute value of p plus ln of the absolute value of k minus p.
Almost. In order for me to integrate this one, I need to do a u substitution. 1 over u, right? But that's k minus p, and p is the variable, so my du gets a negative sign in it, right? So I end up with a minus here instead of a plus. Wait a minute, I'm subtracting logarithms. Ooh, properties of logarithms. Because I hate having 2 ln's on that side. I can't use my e until I only have 1 ln on that side. What's my property of logarithms when there's subtraction involved? I combine and divide. Top, then bottom. So ln of p over k minus p. And now I can use my e. Just like in the last time, I got rid of the absolute value because I put this a here, and the a allows me to be positive or negative, and I'm good with that part. Now, I want to get p all alone, so I can get p of t equals. So there's a bunch of algebra that has to happen here. Fortunately, it's not insanely complicated algebra. I'm going to flip this. K minus p over p equals 1 over a e to the kt. But then on the left, it's k over p minus 1. Wait a second. I have an e in the bottom. What can I do with the e's in the bottom? I don't like having the e on the bottom. I want it out of the bottom. What do I do? Make it to a negative power. One over a is another number, right? I'm just going to change the letter. I'm getting warmer. My goal is to get p all alone. I move the 1 to the other side. And now I flip it again. P over k equals 1 over 1 plus b e to the minus kt. And I multiply that capital K over to the other side, and I have solved my equation for p. Now, remember, these two numbers are given to me in the equation. This one is the one I need to use my initial condition to solve for. Maddie, question?
You still need to keep the negative species.
But I flipped the whole thing with a sum, right? Since I flipped the whole thing, it had to go down exactly the same way. All right, wait a second here. Hang on. My field mouse group didn't have any sort of limit on it. The example in the textbook had a carrying capacity of 1,000 and a growth rate of 0.08. This is the exact problem they gave me in the book. I'm going to add an initial condition. Population at time 0 is 100. So now in my problem, I know that my equation looks like this. Ready? Plug in your initial condition. T is 0, P is 100. E raised to the 0 power is 1. So 100 is equal to 1,000 over 1 plus b. That means that 1 plus b equals 1,000 over 100, which is just 10, which means b is 9. So now I know exactly my population equation. Even if I assume this is for the same field with the mice, then you can tell me what the population is after 4 weeks, can't you? Put in 4, give me a number. .08 times 4 is 0.32. It's negative because it's got that minus sign from the setup. I'm pretty sure this is a whole bunch more realistic than 445,000 mice, 132. But this has got a much slower growth rate, right? 0.08 instead of 2, yes? But even if we were using a faster growth rate, we could still find the appropriate model to fit it. And then graphing this, I'm going to stretch this over quite a range of t's here. So my window is going to go from 0 to, let's say, 25. I need to see y equals 1,000 as my upper limit because that's my carrying capacity. Minimum, maximum. Look, even after 25 weeks, we haven't gotten a very big population, have we? Change my X window, make it bigger. There we go. Now I see, and I see that inflection point at a height of 500, and I see that carrying capacity as we go off to infinity. A much more realistic approach, yes? Again, there are limitations. I picked this one. I knew the carrying capacity was 1,000. I had a physical upper limit derived. But this applies in a lot more places. Let's talk about resource limitations that aren't about fields, right? Let's think of market share. You go out and you introduce a brand new product. Congratulations, you are going to be the next billionaire because of your product. How fast does it saturate the market? Your carrying capacity is 1. Everybody buys this thing. Now, that's unrealistic, right? Every human being on the face of the planet isn't going to own your product. So your carrying capacity might be a little less than 1. But if you you could then look at the growth rate. How fast is your product spreading? What is your advertising efficiency? What is the feedback about your product? How do you deal with it? And then you reach your market share, your penetration of the market. How much of the cellular phone market does Apple own? Does Samsung own? Those are in this sort of growth pattern. Everybody who had one really had already bought one, and making it better with the revisions didn't get a lot better. There weren't new ground-shaking pieces. It tapered off and started to saturate the market. Now, there are other possible models. Even in this sort of growth, we could talk about a harvesting model. Field mice, right? I said that if we had that field of mice growing uncontrollably, at some point every predatory bird in the country would move to this field. So what if we harvest mice? We let the birds in once a week, they take out a bunch of mice. So I could have some number gets taken out with every time period that passes. Fisheries. Anybody here like salmon? Farmed salmon remove a fixed number of fish per tank per week. There's my harvesting model. I could have a maximum threshold. That was our carrying capacity. I could have a minimum threshold. If you think about it, if you have one mouse, how many more are you going to have in 3 weeks? You only have one mouse. It takes 2 to tango here. We're in trouble, right? There's a minimum threshold as well. So I could end up with not just growth at the beginning and our maximum somehow. I could end up with another factor with a minimum involved. Now I've got a cubic equation. My roots don't necessarily hit all the right places, yes? So I'm going to have to figure out how these play together. There are opportunities to bring in trig functions. Why would I do such a thing other than being a sadistic SOB? Well, how many mice are out there having a good time right now? Because it's freezing out there. They're huddled up in their burrow hiding, right? Seasonal variation should be taken into account. So if I have what if I have a factor of t on this side that's related to a trig function? There are all sorts of seasonal behaviors that need to be taken into account. There are models designed to fit lots of different situations. And all of these only involve my first derivative. But this one's autonomous, this one isn't. And if you remember, the very first problem that we drew picture for 2 weeks ago, looked like that. That's not separable. That's not autonomous. How do I solve that? Now here's the best part. The answer is the product rule. But how do I get there from here? That's what we'll cover on Wednesday. Because I can not only do these problems, there are other problems I can't do, like this one. But if I bring something else to the party, I can make this work. By the way, our electric circuit model, that was separable. I prime equals 15 minus 3i. We did that on Monday last. So I know how to solve that using my separable idea. But it turns out there's another way. Easier. Fewer. I think that will be to our benefit. We'll talk about that one on Wednesday. I will see you all then. Have a wonderful rest of your day. Stay warm.